So for this next problem, we want to show that if f prime is continuous and f prime of t is nowhere 0 on the interval, closed interval from a to b, then I want to show that the parametric curve x equals ft and y equals gt can be expressed as y equals big ft, where big F is some function on the closed interval a and b. So notice that it would be really convenient if the inverse function of little f exists. Why? So if f inverse exists, then I can express t as f inverse x equals f inverse ft, the inverse cancel, which is t. So I can express t as a function of x. And therefore, y equals g of t, which is g of substituting this in, g of f inverse of x. So if f inverse is a function, I can put big F equals g composed with f inverse. Then I have y equals big F of x, right? So it would be really convenient if f inverse actually exists. So how do we actually show that it exists? So notice that by the extreme mole value theorem, so let us remind ourselves what EVT is. So it says if f is continuous on a compact interval, AB, then there exists some c and c tilde in the interval AB such that fc is the max of f over the interval AB, and fc tilde is the min of f in the interval AB. So what does this mean for our f prime? So since f prime is continuous on the interval AB, and f prime we know is never 0 on AB, so we have either f prime is larger than some epsilon, which is strictly larger than 0 on AB, or that f prime is going to be less than some negative epsilon, strictly less than 0 on interval AB, where epsilon is some small number larger than 0. So if this is my interval AB, then my f prime must look like either something like this, where it's bounded away from 0 by height epsilon, or it looks like this, where it's also bounded away from 0 by epsilon. Therefore, either f is strictly increasing, or f is strictly decreasing. So the case where it's strictly increasing corresponds to f prime larger than epsilon, and the case where it's strictly decreasing corresponds to the case where f prime is smaller than negative epsilon. So let's assume for now that f is strictly increasing. But what does this mean? It means that for all x that is between a and b, and y that is between a and b, and if x is strictly less than y, then we have fx is strictly less than fy. So in this case, f inverse exists. Why? So we can visualize a function by such a graph. So this is my f, and this is my domain of f, and this is my codomain. So suppose I have like 3 points in this domain and 2 points in the codomain. If my f maps 2 different points to a same point, which is in this scenario, let's call this point P1 and P2. And then let's call these Q1, Q2, and Q3. Then if I go compute f inverse of P2, I have 2 answers, right? It's either going to be Q2 or Q3, because f of Q2 is equal to f of Q3 is equal to P2, right? So in this case, f inverse is not a function, right? Because f as a function maps 2 different points to a same point. But whenever my f is a nice function that behaves nicely, for example, it only maps it provides a 1-to-1 matching in the sense that it maps different points to different images. So so again, this is Q1, Q2, Q3. F of Qi is not f of Qj for all I that is not equal to j. Then f has a defined inverse function, right? It is defined on these 3 points, which is the image of f. Because the inverse of this, there's no ambiguity here, is going to be Q1. So the inverse of the first one is going to be Q1. The inverse of the second one here is going to be Q2. The inverse of the third is going to be Q3. So I can actually define f inverse. So a function with this property is called injective. So injective just literally means that x is not equal to y implies fx is not equal to fy. So what we've observed here is that if f is injective, then f inverse exists as a function. But we know that f is strictly increasing. Which means if x is not equal to y, for example, s strictly less than y, or x strictly larger than y, then I have fx strictly less than fy in the first case, or fx strictly larger than fy in the second case. But either case implies that fx is not equal to fy. So strictly increasing implies f is injective. So f inverse exists. Perfect. Then I can just define my big F to be such. Then we are done. But notice that I can actually relax the condition. Indeed, so fy equals fx is still true, even if f is only differentiable. So I don't need that f prime be continuous. So how do we do this? Again, we want to show injectivity of f. So suppose that f is not injective. What does this mean? It means that there exist x1, x2 in the interval a and b such that x1 is not x2, but fx1 equals fx2. But there's another theorem that we can invoke here, which is the mean value theorem. This says that if f from interval a to b to r is continuous and differentiable on the open interval ab, then there is some c in the interval ab such that f prime of c is exactly equal to the slope of f from b to a. So it means that if this is my b and this is my a, so this is my f of a and my f of b. So this slope here is obtained by some c here. So f prime of c, the slope here is exactly this slope here. So how does this help us? We're given also the condition that f prime is never 0. So if we do have f of x1 equals f of x2. We have the slope fx1 minus f of x2, x1 minus x2 is going to be 0. And so by the MVT, there is some point x tilde such that f prime of x tilde is equal to 0. Right? But then this contradicts the fact that I can't have f prime equal to 0. This is a contradiction. And so therefore, f must be injective. So at this point, maybe you would ask that, is injectivity really necessary for defining an inverse function of f? So recall we had the picture that looked like this. We have 3 points here. And we have 2 of the different points mapping to the same point. So can't we just define the inverse of P2 to be just, say, Q2, right? Can't we just choose one of the pre-images and define it to be the inverse of P2? But this will not work in our problem. Why? Because here we have f prime. So suppose now in our problem, in this specific scenario, that f is not injective. Then it means ft1 is equal to ft2 is equal to some x, 0, for t1 not equal to t2, right? And suppose that I've defined my f inverse of x naught to be t1, right? And what does this mean? It means that f of x is going to be g of f inverse of x is going to be g of t2. Sorry, t1. Right? But then notice that the graph of f of x only gives me the pair x g of t1. This is the only pair on the graph of f. But on the original, curve, I have both x and g of t1 and x g of t2. These two pairs are both on the curve. So by just dropping out one of the pre-images, I am actually losing something with f. So I can never express this curve, which contains these 2 points, as a function, as a graph of the function fx. So this is the reason why we really need injectivity. For example, I can have something like this, right? So this is my x, and this is at t1, and this is at t2, right? So both t1 and t2 correspond to the same x. But then there is no way I can express this graph, this curve, as graph of a function fx. There's just no way, because it does not pass the vertical line test.